At an airport warehouse, Chuck and Kevin check out an ingenious way to handle heavy loads. Dotting a floor with ball bearings greatly reduces friction. Even the heaviest cargoes glide effortlessly.
Floor's covered with these captive ball bearings, just like in the holds of some aircraft. Lets you move huge containers around with ease.
How much do you think this guy weighs?
This weighs 2,300 pounds, as much as a small car.
It's kind of like just pushing something around on a blanket of air.
The team hopes to use this idea in a surprising way to protect a house during an earthquake. At Smash Lab, Chuck and Kevin demonstrate the principle to Nick and Deanne.
Nice. Wow, Kev.
What is that thing?
Captive ball bearings.
Thinking we're going to use this to make a house earthquake-proof.
It sounds like a feasible idea, yeah.
Here's the idea. Earth. And this is the house. Earth moves underneath. The house freely slides on top.
So you're trying to use these ball bearings to create kind of a frictionless surface, right?
Earthquakes shake the ground violently. The team wants to try to isolate a house from ground movement by putting ball bearings between the foundations and the structure above. When riding on a layer of bearings, the house should stay steady, even though the ground below is shaking. Earthquakes are measured on the Richter scale. Quakes of 2.0 and below are rarely felt, but anything above 4.0 can shake buildings and cause serious damage. Earthquake severity rises exponentially. A 7.0 is 50 times more powerful than a 6.0. To show his accomplices what they're up against, Kevin's organized a demonstration.
Earthquake on wheels.
Well, that's pretty cool.
Oh, big hydraulic trailer, huh?
Welcome to the Big Shaker.
The earthquake simulator is furnished like a home to show exactly what happens.
Tapping the mainframe here.
This is the first sofa I've ever seen with seatbelts.
With that bookcase within striking distance, Deanne plays it safe.
All right, Dean, give us a small earthquake.
All right, here we go.
This moderate tremor simulates a 4.0 on the Richter scale. Even at this level of vibration, the contents are scattered, and that's no joke. In real quakes, falling furniture causes more than half of injuries. To prevent this, the team needs to create a ball-bearing system that will keep their test house almost still during a quake.
That's a small earthquake, huh?
Yikes.
Right. Dean, give us an extreme earthquake, please.
Clear.
The next shake simulates an 8.0 on the Richter scale, much more powerful. Deanne hardly stirs. The wheels are doing what they hope their system will do for a house. Isolate it from the movement below.
That's serious,
It's because I'm on rollers. That's why I'm not feeling it.
You know, it looked like it was working pretty well, too. It was sliding back and forth, and we were going the other way, and you were staying pretty still.
Even though that's a simplified version of an earthquake, there's still a lot going on.
Yeah, I noticed two types of movement. There's definitely an up and down and a back and forth movement.
Deanne knows the greatest danger in a quake comes from the ground's sideways motion.
What we're really concerned with is that side-to-side movement, or lateral movement. And it's how much it moves and how fast it moves.
We need to mock up some kind of experiment to simulate that with a house. We're just looking for like a slow motion in one direction and a nice big jerk in the other.
Right. So something powered by a truck or something like that.
Preferably with a house on it or a building of some sort.
That we can topple, right?
Yeah.
Well, let's mock it up.
Why don't we draw this out?
Better than a plan on paper, a Smash Lab impact experiment. The Smash Lab team wants to see if they can come up with a system that will decrease the impact of earthquakes on houses. But first, they want to assess the effect of rapid sideways movement on a building. They're going to set a structure on wheels and slam it into a barrier. On impact, the proto-building should behave as it would in an earthquake. Nick and Chuck rig pulleys for the test, while outside, Kevin has gone cubist.
Come on, Belly. Check it out.
Gotta see what it is.
It's a house.
Wait a minute.
Well, kind of.
It appears to be a box.
Solid walls make the box a lot sturdier.
I'll find the door. Hold on. There is no door.
Or any windows.
Or any features whatsoever.
You guys really want a house I can set you up.
How about a flower box?
There's your house.
For the test, a pickup truck will tow the house on wheels to its fate.
We ready?
Ready.
All right.
Let's get in.
The house is a mess. But that's a good thing. The damage shows how a quake's lateral motion can wrench a building off its foundations.
It was a sudden deceleration, which is much like what you have in an earthquake, when it stops going one way and starts going the other way.
All we wanted to accomplish is see if we could pull it down with lateral movement, and that's exactly what we did.
Yeah.
But what we saw here with the shearing here at the mortar, I think is very representative of what we're going to see in an earthquake. You know, if you have a brick building, all those bricks are going to want to kind of separate apart right here at their connection point.
Scaling this test up to a full-size house in a real earthquake presents problems.
We need an earthquake, and we can't really wait around for one to happen, and we can't just order one up. So we're gonna have to figure out a way to create our own. Well, we need to build ourselves a shake table.
Yes, we do.
Something medium scale that we can try out all kinds of concepts. Reasonably powerful, too. Let's see if we can mock it up some way and play around with it.
We need to play around and make sure our idea works.
The plan is to use hydraulic pistons to mimic a quake's sudden jolts. To check out the idea, they experiment with small pumps, running compressed air backwards through them, creating jerky movements.
Oh, that's great. I think you're onto something.
Strong enough. Ready for a test?
No.
All right. This actually works.
A thumbs up for the pumps. Next, build a compressed air-powered shake table. Meanwhile, Nick and Deanne are designing a model house in the style most at risk in a quake.
A typical American single-story home actually does fairly well in earthquakes. It's when you get multiple stories and you have like a carport or you're missing a wall. Those situations are when homes get structurally compromised and you're a little bit more at risk with an earthquake.
Okay, well, I think we should design in both of those vulnerable points into the scale model.
Including a garage means the ground floor will have most of one wall missing, a much less sound structure. A second story raises the center of gravity, and this extra height further reduces stability.
Okay, let's build it.
On the far side of the lab, Chuck and Kevin finish the shake table. Now they're ready to test it.
Well, let's crank it up.
Their gizmo delivers sudden, unpredictable movements, simulating what happens in a real earthquake. The shake table is ready. To survive, the test house needs protection. The team plans to use what's called base isolation systems that put a damper between house and foundation. To test the concept, the guys rig up a crude arrangement.
This is a good start. The first step on our way to the final base isolation system.
With everything ready, it's time to test.
We have a shake table.
It's cool, huh?
It's violent.
It's a little brutal.
Yeah, I'm a little reluctant to put our little rickety house
Put it on there.
All right.
So the general idea here is we're thinking of isolation systems, right? We want the ground to shake violently back and forth, and we want that house to be standing there unaffected.
And what we got here is the most basic version of an isolation system. It's just ball bearings on a board.
Okay, watch your fingers. Let's test it.
Yeah, that's pretty cool.
It kind of works.
Yeah,
the ball bearings are making the house just roll around a little bit.
Yeah, we definitely have some drifting going on, so that's something we'll need to address. But it looks good.
The ball bearings do isolate the test house from the worst of the shaking, but the whole structure is drifting. They need to hold it in place. It will be hard to harness a full-size house that's riding on bearings. The structure needs to stay still, but it also needs flexibility. A tether that's too weak will snap and the house will pull free. But if it's too strong, it won't allow enough movement and the house will shake, maybe to the ground. Chuck has an idea.
I'm thinking either springs, bungees, maybe you mount them here and here, just to return it back to position. Could be blocks of rubber, anything like that.
But Deanne has a completely different suggestion.
Right, well, we're just looking to restrain it. We can do that with springs, or I think we might be able to do it with gravity. As this ball moves in this dish, obviously gravity is constantly wanting to bring it back to center. Now, there's a system in place under skyscrapers already where they put the entire skyscraper on a bunch of little dishes just like this. And as the earthquake comes, it shakes, but it always comes back to center. Now, granted, a skyscraper is huge, there's a lot of friction, and it's pretty expensive. But I think that we might be able to scale this down to a house.
They decide to develop both systems. It's a contest, with victory going to the idea that works best. Nick and Deanne take a field trip to the City Hall in Pasadena, California. Like many buildings in this earthquake-prone state, it has a base isolation system. They hope it will give them ideas they can adapt for their house protection system.
This is it. Isolation systems everywhere.
Wow.
I can crawl under the entire City Hall of Pasadena.
You can.
It's that isolated. See those old columns there?
Right.
Those are the old load-bearing columns of the building. So they displaced, put these new isolation systems in there, and then cut off those old load-bearing columns.
So what we're seeing in these base isolation systems are, I mean, it's covered up right now with that gasket, and that's just weatherizing it. But it's basically two bowls facing each other like this. So it's a walk, and in the center is essentially this stainless puck. And in the events of an earthquake, the whole system just shifts back and forth and eventually returns to center.
So this building exists completely separate than the ground, and there's just some steel plates linking it to the ground. And this whole building can shift 20 inches, they say. So as an earthquake hits, those two walks will kind of move, and it can displace 20 inches and finally come back to center. The basic technology there is there's a dish, right? And there's a weight in the middle of the dish. And as it goes up, it wants to fall back down. So if we just look at our house design, it's a basic box, put some dishes on all four corners, and just rig it up and see what kind of shapes we want, and see how it's going to perform with a house. Okay, back to the lab?
Back to the lab.
I love this place. I want to stay here and set up an office.
Back at Smash Lab, Chuck and Kevin have run into a problem.
With the springs, I expect it to return to its position, but probably bounce back and forth some. In an earthquake where you have a repetitive motion, they could potentially amplify that motion. Yeah, you see that jiggle back and forth? That's bad.
That's why we can't just use springs by themselves.
Right.
Their system needs more.
So I think we should look at dampers.
Like truck shocks.
Yeah, I mean, that's what they're designed to do. They absorb energy, and they prevent it from the springs from bouncing back and forth.
Most vehicle shock absorbers have two main parts. A spring that flexes, absorbing bumps in the road, and a damper that limits the spring's movement. The damper's piston compresses only slightly as the vehicle's motion forces oil through small holes. The oil's resistance keeps the spring from bouncing too much. A system like this could calm Chuck and Kevin's springs.
We should try making our own dampener here, some sort of liquid hydraulics, but in a much smaller scale than what everybody's used to. Just for use on our mini quake table. Check it out.
Nick and Deanne are trying another approach. putting the bearings in bowl-shaped dishes. It's similar to a system already used in large buildings.
So the general idea here is as we have one big shift, it kind of goes uphill a little bit.
Yep, like this.
But because of the nature of the dish, it's going to kind of rock back downhill.
Exactly.
So it's kind of natural equilibrium.
Exactly, yeah. And we'll have 4 points of contact
Great.
around this thing, so.
This system exploits gravity. The action of an earthquake will send the bearings up the side of the bowl, but not too much. Gravity will limit their upward motion and keep the house centered. Time to go down to Shaky Town. Well, Shaky Table anyway.
All right.
Should we give it a go?
Yeah, give it a go, just by itself.
Jumping. If we add more weight, we're going to get a little more friction in there.
Okay, so it came off the platform, but this is clearly too light.
Yeah, I mean, the thing with a friction pendulum design is they're typically used on skyscrapers. That's why they work so well. Is there's so much weight from that skyscraper pushing down, creating that friction that's necessary to kind of keep this in place.
Right. And actually, this model at scale is a lot lighter than the actual house would be. So I think it would be fair for us to add maybe a few weights, like sandbags or something like that, to weight it down.
Yeah.
And get a little closer to reality.
The increased weight keeps the bearings in the bowls, but the house is still moving too much. Deanne thinks the bowl's shape may be to blame.
It's definitely better. It's kind of going uphill a little bit and coming back down. But if that was a lot more concave, there'd be a lot more gravity to fight. Like in this case, it's fairly shallow. So you're not fighting all that much gravity. And let me just geek out for 1 second, okay? So...
Calculating curves is a maths problem, right up Deanne's street.
So what this...
Meanwhile, Chuck and Kevin are nearly ready with the shock absorbers.
This is too loose, and it's just letting the air escape right past it. Teflon tape, it's very thin, and it slides easily. Oh, yeah, that's great.
You can tell it makes a difference? I'm sure.
Yeah. You can... There's 5 holes, so we can cover up any number of the holes and get different amounts of damping. Okay, works pretty well. Looks like we've fashioned ourselves a pretty decent damper.
Let's take it to the shake table.
The shocks are installed.
Attracted?
Let's see if it works.
You sure?
Yes.
Definitely dampers make this whole system work.
Yeah, it quiets the resonance, so it doesn't just sit there and spring back and forth all day.
One boop, another, right back to its original position. Springs and dampers.
Spring and damper systems should work on a larger scale too. Across the lap, Deanne solves the bowl equation. She knows just the right curve that will hold the bearings.
So this is it, 88 inches.
So we need an 88-inch arc on a ramp, basically like a half pipe.
The perfect arc, a precise slope that should prevent the bearings moving too much.
Let's build it.
The shake table will only move in one direction, so for their test, they don't need an entire bowl. A cross-section will do.
All right.
5.
Oh, you're timing it?
I went 1, 2,
okay.
3, 4, 5.
Gravity does stop the movement, but not quickly enough.
Let's see if my weight makes any difference. 2, 3, 4.
They're going to need more than weight to damp the system.
We want to actually dampen the response, then we do need to introduce friction.
Well, why don't we actually add something to this substrate, like rubber?
Yeah, let's give it a go.
Just lay 'em.
A rubber layer may add friction, reducing movement.
Wow. Success!
I love it! I think we should do one last thing. I think we should actually move the ground as opposed to moving the platform.
This test pits their system against real motion. The pole won't move, but Deanne is floating free. If the system isolates her from the movement below, her head will stay near the pole, proving that the system works.
I don't think I'm moving! You are the best earthquake ever!
Thank you.
I was staying right here. I was completely isolated.
Perfect. Well, this is basically a smaller representation of what we'll do on a large scale then.
Scale it up, two-story home.
Yep.
Bring on the earthquake.
The two rival ideas both seem to work, so the teams decide to take both to full scale. But before Chuck commits to such a massive engineering project, he has one last check to see that his concept's going to work.
The big problem with a shake table is figuring out how do you shake it. And one of the ways you can do that is with a hydraulic system, but I think we ruled that out because the control architecture for all of the controls for the hydraulics would be too complicated. So as a simple approach, we're going to take a couple of big horsepower motors and just mount a crank so it rotates. As the crank rotates, it pushes the table back and forth. So we turn the rotary motion of the motor into linear motion on the table. And so it works kind of like this mock-up that I have, but this is just a way to experiment on a small scale so I can try a few different concepts out and see how it works.
And once the concept has been established, it'll ride the giant shake table. The Smash Lab team has devised two ways to quake-proof a house. Now they're ready for full-scale tests on a gigantic shake table.
Success!
I love it.
All right.
Okay, we're good to go.
A little more, Gadget, bring it. Hold that.
We need more over here. We need more over here.
The team needs some construction assistance.
Just tack one end and then get the other one on.
Every time you fix your end, my end goes wrong.
Well, we'll just
Every
tack.
time I fix my end.
And to go with the shake table, construction begins on full-scale houses. Each ground floor is missing part of a wall, representing a garage door. A second story adds height, raising the center of gravity and reducing stability.
So the structural integrity of this house really lies in the strength in numbers type of thing. So all the individual fasteners on the clapboard, the drywall are really what's keeping it together. So when the structure becomes fatigued, it's really going to start to fail here. And once that happens, the thing is just going to catastrophically fall apart. And hopefully, our base isolation system is going to prevent that from happening.
These houses will be subjected to the same ground movement that was caused when a quake rocked Northridge, California in 1994. At 6.7 on the Richter scale, it wasn't one of America's strongest earthquakes. But the ground movement set a speed record, making Northridge one of the most destructive quakes in US history. The test tremors will come courtesy of a 6-meter square shake table that the team has constructed. A 100 horsepower motor will shake the foundations.
Can we turn that on and see how it's running?
Chuck's faith in his earthquake machine is severely tested when he and Kevin finally fix the link arms.
Oh, dude. Kill it.
There's a serious problem.
You can see it wobbling.
Oh, yeah.
The shaft is just wobbling up and down. The whole frame, back and forth.
One of the link arms is not straight, causing a dangerous wobble.
Okay, so we just gave it a run, and I'm nervous. We saw the shafts wobbling, and a good, almost 3/8 of an inch. It's scary as hell. The shaft is a 2-inch thick steel shaft, and if the thing is bending, this thing is under some serious binding force, and that's bad news.
They've got to get to the bottom of the problem, or there'll be no test.
I think it's got to be in the offset system. So what we need to do is just find a smarter way of calibrating this thing. So I think if we get one of these mounted on here, we can just have a nice close comparison between something not moving and something moving. We'll be able to see it as it's warping around, how far off it goes.
This is the tight part.
Yeah, it's coming this way now. And now it's going back that way. But if the shaft is just wobbling back and forth some, that doesn't bother me so much.
As luck would have it, the problem is geometric.
All right, turn her on, man.
Yeah, so what's going on is these two outside shafts that are welded to the offset plates, are just slightly misaligned and not quite on line in the center of the shaft.
So what's important is that this main shaft in the center, it's straight.
That's fine, though.
They're back in business.
I'll kill the power.
The table only moves sideways, not up and down, but its movement does simulate the destructive lateral forces of an earthquake.
It goes back and forth as far as we want it or as little as we want it, and we can shake it as fast or as slow as we want it. It's pretty cool.
This is really something to behold.
Gearing, crank arms.
Yeah, it's beautiful.
I think we should try to maybe scale up small, medium, large on the earthquake size,
Right.
and then also trying to kick a big peak ground acceleration to try to rip the house off its foundation.
Deanne calculates the parameters needed to simulate the Northridge quake's lateral movement.
We're going big time.
They'll run the table for 15 seconds, the same amount of time it took for tremors to damage 25,000 homes in the Northridge quake. The first test will reproduce the force felt by a typical house 65 kilometers from the epicenter. The second will show what happened to homes close to the quake's source. If the houses survive, they'll both be subjected to a third set of tremors, worse than any earthquake ever recorded. It's time for the test.
All right, so we have to make 4 roller plates to go in each corner of the table.
Yeah, and the house is pretty big. We've got each of these plates cut, and if we just mount these plates on the underside of the house and then have a surface for it to roll on, it should work.
At each corner of the house, they'll weld plates that hold bearings. Those low-friction surfaces should isolate the house from any ground movement. Shock absorbers will keep the house on the table and dampen movement. But every bearing has to touch the base, or the system could fail.
The problem is we've got these 700-pound capacity roller bearings.
Yeah.
And which means we're going to have to use
A lot of them.
A lot of them per corner.
Right.
And the problem with that is it's possible to warp the steel a little bit and have maybe only 1 or 2 contacting. And if that's the case, they'll fail because they can't possibly handle that load.
But Chuck has a simple solution.
What we have is a rubber sheet. It's just some polyurethane rubber put on there, and then we bolt all these to the plate. The rubber should give us a little bit of give, so the one that's sticking a little too far out gets compressed, and they all equalize in force.
Yeah, when the weight's coming down on one of these ball bearings, the rubber's just going to squeeze, so they're all even instead of just 1 or 2 touching. They're all going to touch now. The rubber's underneath.
I think it's a decent workaround.
Nick and Deanne also have their isolation system just about ready.
All right, so we adhered. I can already feel the dampening happening. It's beautiful. So we just need these mounted to the undercarriage of the house.
They're setting ball bearings at the corners. Concave runners hold the bearings in place. When the shaking starts, the house should ride in the runners. If the motion is transferred, the gentle rise and fall of the house should prevent catastrophic shaking. Rubber on the runners adds friction, further reducing movement.
So this is it, huh?
All right.
Simple, but beautiful, and it's gonna work like a charm.
I can't wait to see it work.
Sounds like your house shaking back and forth is going to look a little different from our house shaking back and forth.
They go up and down, too.
Yeah.
If this rubber works like we want it to, it's actually going to isolate it, and hopefully it'll stay a lot more still than we saw with you guys.
It'll hopefully just do this. Just a little bit.
First up, Kevin and Chuck's system.
All right, we have our crane, ready to put our house on the shake table and see what happens, and I'm pumped about it. I can't wait.
You wanna push your corner? We gotta rotate this, yeah?
Both teams' ideas have to face reality, and all those bearings have to touch the table or their systems won't work.
Hey, Kevin, check those balls over there. Are they all touching?
Oh, yeah.
That's cool, huh, Kevin?
Yeah, it works.
Okay, so we just need to get this thing welded and get the shocks on, and we're good to go.
Excellent.
Then we can start shaking.
The shock absorbers are attached.
All right, it's not very far. It's only 1.5 inches.
Chuck and Kevin are hoping they'll dampen movement and keep the house from sliding.
Almost. There it is.
Well,
I think this is it.
I say we try it.
One last job. Some interior decoration. To pass the test, each house has to stay intact, with its contents in place.
Oh, it feels comfortable in here now.
I like that.
Yeah, I like that feeling once you first get moved in, you know? You get up, boxes unpacked.
All right, guys, no horsing around. Let's shake this bad boy down.
All right.
First time around, the house will shake back and forth 3 centimeters for 15 seconds. That's what happened in neighborhoods 65 kilometers from the heart of the Northridge quake. Time for final checks.
So we've got everything set up. You guys ready?
Oh, yeah.
Can't wait.
Okay. So the first test.
Wussy earthquake is what I say.
Passing car.
We gotta start small.
I know, you're right. You're absolutely right. And this is the shakedown test for the shake system, too. So we don't want to overdo it with the first one. All right, let's get it rolling. All right, power on. You can see the base isolation system working.
Yeah, it's working. The house is still definitely moving, though. You see that?
Oh, it's moving. I expect it to be moving.
See it actually flopping a little bit?
Question is it moving more gently than the house? Okay.
That was nothing.
Success. Maybe. The house survived. But what about the decor?
Whoa! You guys should see it up here. Nothing happened. Really? Nothing.
Chuck and Kevin's system passed with flying colors.
Okay, so that was pretty light earthquake, just like we expected.
No sweat,
Easy
man.
peasy.
The isolation system was working. You could see those springs compressing and letting go.
Totally. Even that long, thin flower pot was still standing up straight.
Oh, was it?
Yeah, nothing moved.
If that isolation system wasn't there, it would have done a lot more damage upstairs.
Oh, for sure.
You saw the whole house going back and forth and responding. Like, you can't underestimate the power of what we've done.
Now Nick and Deanne submit their house for a moderate shaking.
We don't want to be on the rivets.
I'm inside. I'm on the inside rivet line.
Okay.
When the steel hits the rubber, there's big trouble.
So it's a bit alarming. We got a little more slop in that rubber than we wanted.
It's the ripple effect. And it could end catastrophically with a tear.
We're going to see it.
Yep.
And if there's a problem, we'll cross that bridge when we come to it.
It's too late. There's no going back. Furnishings in place, the house awaits the shake. All eyes are on those mounts.
All right, power on.
And speed.
As they feared, the bearings are ripping the rubber.
So you can see the rubber tearing up on the other side there. See it?
The house survives, but the system is damaged.
How's it look over there?
That's bad news, huh?
Yeah, we put a hole directly through. Not the most desirable response.
Yikes.
That's too bad.
I say we slice it off entirely, just pull it out.
But you lose your damping system.
I think we can still get there with just the pendulum itself.
But all is not lost.
Plants up, the lance up, even the bowls are still on the shelf.
No damage to house or contents, meaning they'll be subjected to even more abuse. To simulate the epicenter of the Northridge quake, the team sets the shake table to shimmy 10 centimeters for 15 seconds.
Guys, staying up or coming down?
Staying up.
Absolutely staying up, man. Everything was standing up upstairs. I mean, if anything fell, I might have some doubts, but everything was upright.
It's staying up.
Chuck and Kevin's system is first in line for the Northridge epicenter treatment.
This is the one we need to succeed at. This is the one that you see on TV and all the houses are down, a lot of damage. This is the one everybody worries about. If we can succeed here, we have great base isolation systems.
Okay, you guys all set?
Go ahead, Kevin.
Powering on.
Whoa!
Yeah, look at that. That's cool.
I thought it was doing this a little bit, but it's doing that.
Flex now, you see that?
Oh, yeah, look at that whole wall's bowing.
Oh, yeah.
And 3, 2, 1, end time.
But it's up.
Walls and windows moved, but the house stayed intact. Inside, the news is not as good.
Oh! Not quite the same story.
All right, all right. We have some fallen bookshelves up here.
The vase is down. The bookshelf is down.
Oh, yeah, but if you were sitting there, that wouldn't have been so fun.
Yeah, that'd have been kind of chaotic, you know, watching your favorite movie or something like that. Just with
The
that thing probably just came down.
largest-
This is kind of top heavy.
Most
Dangerous.
injuries and most fatalities in an earthquake are just due to things falling on top of you.
Yeah, and
It's really not because of structural damage to a house.
The shelves took a nosedive, but the house survived a force equivalent to that near the epicenter of the Northridge earthquake. The bearings and shock absorbers performed proudly.
I'm really impressed. Those isolation systems, it's beautiful. I hope ours does that well.
Nick and Deanne's system will go through the same ordeal, but now with no rubber pad for added friction.
All right, so this is a real test.
This is it. Medium intensity, 4 inches this time.
Major earthquake.
Let me guess, you guys are feeling confident.
Very confident, yeah.
Yeah.
Deanne?
I'm confident.
All right,
Yeah.
she's confident.
I'm
It'll be a
confident.
good time.
Ready?
Fire it up. Power on. And speed.
Look at that!
That's so cool!
Oh my God!
Beautiful. It's totally still, isn't it?
No problems. Even with no rubber pads, this system isolates the house from the tremors.
That is an isolation system, boys!
And time.
You can let it run
Like
all day,
isolated
though.
inside.
It's amazing!
Let's go look at it.
And inside,
It's almost in perfect condition.
Yeah, what? Plant's still up. Alarm clock is fine.
Cardboard box down.
So the base is down, but I think that's actually when it started to slow,
Yeah.
and you know the ball bearings grabbed the pendulum.
Great.
Nice job, guys.
Come on.
done.
Admit
Well
you're
done.
impressed. Admit
Oh,
you're
I'm great.
impressed.
Oh, this is
How
great.
beautiful was that?
That was a pleasure to watch.
each system has excelled. So far, both successfully cushioned a house from a simulated 6.7 magnitude quake. But which works best? It's time to take them to the limit and beyond, into a realm nobody has ever had to live through. 2 earthquake protection systems, and both of them stood up to simulated earthquakes measuring 6.7 on the Richter scale. The Smash Lab teams are on a roll. Now it's time to dial the shake table to its highest setting. The table will move back and forth 20 centimeters, twice as far as it did in the previous test. This will simulate a quake larger than anything on record. At 10.0 on the Richter scale. It doesn't get any bigger than this. Chuck and Kevin's system has done well up to now, but it started to buckle in the last test.
You guys ready to rock and roll?
Yeah!
Okay, power up.
The top's not
At the start, all's well.
Very nice. Oh my God!
You gotta be kidding me. Just let it crank. Just let it crank.
Oh, the stairs fell out.
Double time. All right, time. Time off.
That was 15 seconds. It went down to the 15th second. Okay, let me pull this panel off.
It's like a drywall disaster.
Yeah, I can
zone.
make no sense of that.
There is our couch.
There's the couch.
The house collapsed, but it's not a total disaster.
Rug is up here. The table's still standing on 4 legs, though.
Right.
You know what? The top had 4 walls. The bottom only had 3.
It did.
So I think the structure is completely compromised with the 3 walls.
I think
And
it
up
is.
top, it was kind of staying as a box, just like a weight on
Yeah.
top.
Hey, good job, guys, though. I mean, the isolation system worked until the very end. That was the 15th second. So you actually made it through the 15 seconds. But, I mean, it wouldn't have been a fit structure to live in.
I
after
would
that.
not want to have been in there.
That last one is off the charts.
Yeah, it doesn't happen.
And it stood up for a while. That isolation system was working.
Let's clean this mess up.
Clear it out.
And get the other one loaded up on here and see how well yours does. Good luck.
Yeah.
You guys set the bar high.
Next, Nick and Deanne's house.
I'm incredibly confident on this. I mean, seeing how well it responded to the last and middle test, which is basically our challenge.
But this one is a lot more.
I know, it's a lot of power.
Isn't it like a factor of 5 or something like that? Like ridiculous?
Well, there's only one way to find out what happens here. But now, you're absolutely confident, and you are?
I'm a lot more confident than I was before.
I don't blame you.
I'm pretty confident too, but I still think it's coming down.
Confidence is high, but will their system perform?
Power up!
It's perfect!
The quake shakes off the scale, but the house barely moves.
Look at that!
Time! Watch it slow down now.
Yeah, I know. This is where it gets a little ugly.
Then it starts going back.
Not too bad.
Oh, I mean...
Good job, guys.
After 15 violent seconds, the house remains intact. And the contents?
Look at that. It's just a vase. Just about perfect. Even the alarm clock's still up.
That's amazing.
That is great. That is totally amazing. And look at how easy it is to push this vase off. It's just, you know?
It's like nothing.
Yeah, it's like nothing. The most damage we saw was actually from the first test, which seems ironic, but...
I know, the smallest one. But as soon as we got more acceleration, it completely isolated.
In the test that simulated a 6.7 earthquake, both ball-bearing base isolation systems succeeded. As they analyze footage in the lab, the team compares notes.
Ours did pretty well, but yours, unbelievable. I gotta hand it to you guys. That system, it was like your house wasn't even moving at all. It barely moved.
I think it proves that a base isolation system can be applied to a house. I mean, the whole premise, right? The ground is shaking violently, and the house is isolated, not moving at all.
Yeah.
And the coolest thing is that this technology can actually be implemented into new home construction feasibly.
If it can be incorporated into construction methods, this approach could offer a simple way to counter a major threat to life and property.